You're standing in the middle of a vast desert. The sun beats down mercilessly. There hasn't been rain in months. Yet somehow, an entire civilization is thriving around you, complete with gardens, agriculture, and thousands of people living comfortably in one of the driest places on Earth. How is this possible? The answer lies beneath your feet. Hidden underground are massive chambers, carved into solid rock, some large enough to hold an Olympic-sized swimming pool. These are cisterns, and they represent one of humanity's most ingenious solutions to survival. Here's the surprising fact. In the ancient city of Petra, the Nabateans constructed over 200 cisterns and reservoirs, connected by more than 200 kilometers of pipes. Some of these cisterns are still functioning today, over 2,000 years later. That is not just impressive engineering, that is a testament to knowledge we are only now beginning to fully appreciate. Today, we are going deep literally into the story of how underground water storage transformed human civilization and why these ancient technologies might hold the key to our water-scarce future. To understand why cisterns were revolutionary, we need to understand the fundamental problem ancient peoples faced: water scarcity and unpredictable climates. The ancient water crisis. The earliest evidence of cistern technology dates back over 5,500 years to the Neolithic Age. This wasn't a coincidence. As humans transitioned from nomadic hunting and gathering to settled agricultural communities, they encountered a critical challenge. Crops need consistent water, but nature doesn't provide it consistently. Rain falls seasonally. Rivers flood and dry up. Springs can disappear. Yet communities needed year-round water supplies for drinking, cooking, bathing, and most critically, agriculture, the foundation of civilization itself. Early innovations. The Minoan civilization in Crete developed sophisticated cistern technology during the early Bronze Age, around 3500 to 2150 BCE. These weren't simple holes in the ground. The Minoans understood that water needed to be protected from contamination, prevented from evaporating in hot climates, kept cool for consumption, stored in quantities sufficient for entire communities. The engineering challenge. Building an effective cistern required solving multiple problems simultaneously. First, the waterproofing problem. Water seeps through most rock and soil. Ancient engineers needed to create impermeable barriers. The Nabateans, for instance, developed specialized waterproof cement to line their cistern cement so effective that many of their cisterns remain watertight today. Second, the collection problem. How do you gather enough water? Ancient engineers designed sophisticated catchment systems. They carved channels into hillsides to direct rainwater. They built gutters on buildings to capture roof runoff. They constructed dams to divert seasonal floods into storage. The Romans took this to extraordinary levels. Their domus houses featured an impluvium, a sunken courtyard basin that collected rainwater and funneled it into underground cisterns. This wasn't just about water storage. The system also filtered, cooled, and ventilated the entire house. Third, the distribution problem. Water in a cistern is useless if you can't get it out efficiently. Ancient engineers developed clay pipes, aqueducts, and ingenious pressure systems to move water from storage to where it was needed. Why this mattered for agriculture? Agriculture in dry climates was impossible without water storage. You couldn't simply plant crops and hope it would rain at the right time. Cisterns allowed farmers to irrigate during dry seasons, support crops through droughts, cultivate land far from natural water sources, sustain populations in otherwise uninhabitable regions. This wasn't just about convenience, it was about survival and the expansion of human civilization into new territories. Let's explore 3 remarkable cistern systems that reveal just how advanced ancient water technology truly was. Case Study 1. The Nabatean Water Empire. The Nabateans were desert nomads who transformed themselves into master hydraulic engineers. Their capital, Petra, located in modern-day Jordan, was built in one of the most water-challenged environments imaginable. Yet researcher Charles R. Ortloff was able to reconstruct their hydraulic network and discovered something astonishing. The system included 8 water sources, 40 dams and water reservoirs, and over 200 cisterns. The network of pipes exceeded 200 kilometers in length. But here's what makes this truly remarkable. These cisterns were designed with secrecy in mind. The Nabateans understood that water was power. By controlling hidden water sources throughout the desert, their camel caravans could cross vast distances without relying on water wells controlled by rival tribes. This gave them a decisive trading advantage. The cisterns themselves were carved into strategic locations throughout Petra and the surrounding area. They captured and stored diverted rainwater from flash floods, a particularly clever adaptation because desert flash floods, while dangerous, represented enormous volumes of water that would otherwise be lost. Many of these cisterns still function today, proving the exceptional quality of Nabatean waterproof cement and construction techniques. Case Study 2. The Basilica Cistern of Constantinople. In 532 AD, Byzantine Emperor Justinian I commissioned one of the most spectacular cisterns ever built. The Basilica Cistern in Constantinople, modern-day Istanbul. The scale is breathtaking. 138 meters long by 64 meters wide, supported by 336 marble columns arranged in 12 rows. This underground palace could hold approximately 80,000 cubic meters of water, enough to supply the Great Palace and surrounding areas during sieges or droughts. The cistern wasn't just functional. It was architectural art. The columns were repurposed from ancient Roman structures, and the space creates an almost cathedral-like atmosphere underground. It demonstrates that ancient engineers understood the psychological and cultural importance of water infrastructure, not just its utility. Case Study 3. Ancient Jerusalem's Water Network. Jerusalem's water management system evolved over centuries. But by the late Second Temple period, the city had developed extensive storage capacity to support a growing population and accommodate the influx of pilgrims. Nearly every building, both private and public, had its own cistern. The city also maintained several large public pools and reservoirs. This redundant, distributed system was crucial for a hilltop city far from major water sources. The cisterns collected rainwater during winter rains and supplied the city through the dry summer months. The Roman concrete connection. Now, here's where the story gets even more fascinating and connects to recent scientific discoveries. When we examine ancient Roman cisterns and other water infrastructure, we find they've survived for over 2,000 years with minimal maintenance. Modern concrete structures often deteriorate within decades. What did the Romans know that we've forgotten? Recent research led by the Massachusetts Institute of Technology, published in Science Advances, uncovered a remarkable secret. Scientists at MIT and Harvard University discovered that Roman concrete contains calcium-rich mineral deposits called lime-clasts, small, white chunks that appear throughout the material. For years, modern engineers assumed these were impurities, signs of poor quality control. But Professor Admir Mezik at MIT questioned this assumption. Why would Romans, who meticulously perfected their recipes over centuries, accept sloppy mixing? The team conducted experiments, creating concrete samples using both Roman and modern methods. They deliberately cracked these samples and ran water through the cracks, simulating the kind of damage cisterns and aqueducts would experience over time. The results were stunning. The samples made with Roman techniques, containing lime-clasts, completely self-healed within 2 weeks. The cracks sealed themselves through a chemical process, and water no longer flowed through. Meanwhile, modern concrete samples without lime-clasts never healed. The difference? Romans used quicklime, a highly chemically reactive form of lime that enables self-healing. This technology was ideal for water infrastructure like cisterns, where cracks could develop from ground movement or pressure changes. This discovery helps explain why structures like the Pantheon, which contains the largest unreinforced concrete dome in the world, and countless Roman cisterns have endured for millennia while modern infrastructure crumbles. Understanding ancient cistern technology isn't just about appreciating historical achievement. It matters urgently for our present and future. Climate resilience. Ancient civilizations faced climate variability without modern technology. They couldn't pump water from hundreds of miles away or desalinate seawater at scale. They had to work with what nature provided, using intelligence and engineering to maximize every drop. Today, as climate change creates more extreme weather patterns, longer droughts, punctuated by intense rainfall events, we face similar challenges. Conventional water infrastructure often can't handle these extremes. Reducing carbon emissions. Here, as a sobering fact, modern cement production accounts for approximately 8% of global greenhouse gas emissions. That's more than the entire aviation industry. Every time we build water infrastructure using conventional concrete, we're contributing significantly to climate change. The MIT research on Roman concrete reveals that ancient self-healing materials could create more resilient infrastructure that lasts centuries instead of decades. This means less frequent replacement and repair, reduced cement production, lower carbon emissions, better long-term sustainability, water security. Groundwater depletion is accelerating worldwide. Aquifers that took thousands of years to fill are being drained in decades. Meanwhile, rainfall patterns are becoming less predictable. Cisterns' modern versions, inspired by ancient designs, offer a way to capture and store rainwater locally, reducing dependence on overtaxed groundwater supplies and vulnerable centralized water systems. Agricultural sustainability. Agriculture consumes approximately 70% of global fresh water. In water-scarce regions, the revival of ancient agricultural terrace techniques, combined with cistern systems, represents a pathway to sustainable farming. The Nabatean approach capturing flash floodwater in cisterns and using it for terraced agriculture is being seriously reconsidered by modern researchers as a model for future food production in arid regions. The revival of cistern technology is already underway globally, and the results are promising. Urban rainwater harvesting. Cities worldwide are rediscovering rainwater harvesting. Modern buildings are being designed with integrated cistern systems that capture roof runoff for non-potable uses like irrigation, toilet flushing, and cooling systems. Studies show that rainwater harvesting can remain reliable even under climate change scenarios. Research indicates that even in arid regions, properly designed systems can maintain high reliability despite changing rainfall patterns. Climate change adaptation. A 2018 study on rainwater harvesting systems found that climate change would have minimal negative impact on system reliability when designs account for regional climate zones. In some cases, increased rainfall intensity, even if total annual rainfall decreases, can actually improve collection efficiency. The key is designing systems based on ancient principles: distributed storage, catchment optimization, and resilient materials. Flood management. The ancient Nabatean flood control system in Pietra demonstrates sophisticated understanding of urban water management. Modern researchers studying these systems suggest that reviving ancient techniques could help manage flash floods in contemporary urban areas. Rather than treating stormwater as waste to be quickly channeled away, ancient cistern systems captured it as a resource. This dual-benefit flood mitigation and water storage is increasingly relevant as cities face both flooding and water scarcity. Development Goals. Rainwater harvesting contributes directly to the United Nations Sustainable Development Goals. It provides reliable water supplies to remote and drought-prone regions, reduces dependence on mains water systems, and offers substantial environmental benefits. In communities lacking centralized water infrastructure, cistern systems modeled on ancient designs offer a lower cost, more sustainable alternative to expensive pipe networks. Material science revival. The MIT discovery about Roman concrete's self-healing properties is now informing new material development. Engineers are working to recreate quicklime-based concrete formulations that could make modern cisterns and water infrastructure dramatically more durable and sustainable. If we can build cisterns that last 2,000 years instead of 20, the environmental and economic implications are profound. Let's return to where we started standing in that desert, wondering how ancient peoples thrived in impossible conditions. The answer wasn't magic or luck. It was engineering, observation, and profound understanding of natural systems. Ancient builders watched how water flowed, where it gathered, how rock formations could be shaped to channel and store it. They tested materials, perfected techniques, and built systems that outlasted their empires. Those cisterns carved into rock weren't just storage chambers. They were acts of hope, declarations that human intelligence could overcome environmental constraints. They were investments in future generations, built to last not years, but millennia. Today, we face our own water crisis, amplified by climate change and growing populations. We're learning, or rather, relearning that the solutions might lie beneath our feet, in technologies our ancestors perfected thousands of years ago. The story of cisterns teaches us that sustainable technology isn't always about innovation. Sometimes it's about rediscovery. Ancient peoples solved problems we're still struggling with, and their solutions were often more elegant, more durable, and more environmentally sound than ours. When we study how the Nabateans stored water in the desert, how Romans created self-healing concrete, how Byzantine engineers built underground palaces of columns, we're not just looking backward. We're finding pathways forward. The next time rain falls, consider this: that water could be captured, stored, and used months later to grow food, sustain communities, and build resilience against an uncertain climate. That's not ancient history. That's our future, if we're wise enough to learn from the past. Because the real lesson of cisterns isn't just about water storage. It's about thinking long-term, building for centuries, and recognizing that the most sophisticated technology is sometimes the simplest rock, cement, gravity, and human ingenuity. The ancient cisterns are still there, still working, still holding water after 2,000 years. They're waiting to teach us if we're ready to listen.